Hello students, today we'll talk about electric potential of a charged spherical shell. Earlier we had a topic in which we found out electric field due to charged shell, and today we'll see how to determine electric potential due to spherical surface charge distribution. So let us start. To understand today's topic, we need to know the basic definition of electrostatic potential. We know that if you want to find out electric potential of charge q at some point A, the basic definition says that potential is work done per unit charge. You substitute the work done formula, and what you get is negative integration of electric field over dr from infinity to given point. Here it is A. So, depending on the point, this A will change. It may be P or B or any other symbol. But essentially, we are coming from infinity, and negative sign indicates that electric field and displacement both are in opposite direction. Apart from this, we also need to recall electric field due to spherical shell. We know that if charge is distributed uniformly on spherical surface, inside the spherical surface electric field is zero. There is no electric field due to the surface charge inside the shell. And what if we are outside the shell? If charge is distributed on some sphere only on surface, and if we want to find out its electric field at some point outside the surface, it is given as kq by r square, or sigma into radius square upon epsilon 0 into distance square. But we'll consider it to be kq by r square. It is very similar to electric field of point charge. So with this prerequisites clear, we can start with today's topic. Let us start. So consider a shell of radius r, and let there be some positive charge on its surface. So we have a charged spherical shell of radius r. Let the total charge be capital Q. We'll denote the charge by capital Q. And we want to find out electric potential due to this charged spherical shell, where, say, at point P. So this is the point where we want to find out electric potential due to capital Q charge distributed on some spherical shell. How far is point P? Let the distance be smaller from center of the shell. And how do we determine electrostatic potential? So as per definition, it is work done to bring unit positive charge from infinity to given point P, isn't it? So if you don't have unit positive charge, what to do? Suppose I don't have plus 1 coulomb charge, I have 2 coulomb charge. So fine, no problem. You find out work done with 2 coulomb charge. You come from infinity with your 2 coulomb charge and divide work done by 2. Suppose if you have 5 coulomb charge, you come with 5 coulomb charge from infinity to given point and divide your answer by 5. So for now, we are bringing q coulomb charge. We have q coulomb charge. We'll take it at infinity, and from there we'll come to point P. We'll see how much is the work done, or we'll use the other form of potential, integration EDR, and that is how we'll find out electric potential at point P. So when we come from infinity to P point, we know that electric field is kq by r square. At outside any point outside the shell, it is kq by r square. But then it means that electric field at different point on the path is different, because r distance is different, so electric field is varying, and hence we have to integrate EDR. So let us see how to find potential at point P. So according to the definition of electric potential, V at point P can be given as negative integration of EDR from infinity to P point. And what do we need now? We have everything. See, we know electric field, it is kq by r square, and then we just need to integrate. So potential at point P can be given as negative integration of kq by r square by dr from infinity to point P. Kq being constant can be taken out, and integration of 1 by r square will give us minus 1 by r. So substitute upper limit, lower limit, 1 by infinity will be 0, and hence the potential will be kq by r. Don't get confused, this r is the distance of the point where we are finding out potential from center of the shell. Now this is very similar to potential of point charge. If you remember potential of point charge, it is also kq upon distance. Similarly, shell behaves like point charge. When you are at some point outside the shell, the behavior of shell is very similar to point charge. Electric field of shell is kq by r square, just like point charge, electric field of point charge. Similarly, potential of shell is kq by r, which is very similar to potential of point charge. So at any point outside the shell is behaving very similar to that of point charge. Its behavior is similar to that of point charge. But what if point P is inside the shell? Would the answer be same if P is somewhere inside the shell? Let us check it. So again, we have the same shell of radius r with charge capital Q on its surface, and now we consider point P somewhere inside the shell. Again, let the distance be r, and we want to find out potential at this point P. So again, process remains same. What is the process? Take some charge Q, come from infinity to given point, and look at the work done. Okay, come with your unit positive charge from infinity to point P and look at the work done. That is the potential of point P. Now there is one problem. What is the problem now? Problem is when we come from infinity, the electric field in this part is kq by r square, whereas electric field from P to surface is not kq by r square, it is 0. It means that we have to have separate calculation from r to infinity, from surface to infinity, and from P to the surface. This part and the other part outside the shell are having different values of electric field. So we cannot find out infinity to P integration in one go. If you take infinity to P E d r, E value is different, and hence we will have to divide the integration. So maths will be a little bit lengthier as compared to previous case, but not very difficult. So when we come from infinity to the surface, electric field is kq by r square. From surface to point P, when we go, electric field is 0. So for this situation, how do we find out potential at point P? Let us see. So again, we'll follow the basic definition of electric potential, which says that potential is negative integration of electric field by dr from infinity to point P. And as we have different electric field, we'll divide the integration into two parts. First, we'll come from infinity to surface, that is infinity to r, and then we'll go from surface to point P. Okay, because electric field here is kq by r square and electric field inside is 0. So let us substitute values. Inside electric field is 0, so this integration becomes 0. So we have only one integration to deal with, and very similar to previous case, kq is outside, 1 by r square on integration will give minus 1 by r, and then we have our answer kq upon r. Which r we have now? This is radius. What does it mean? It means that instead of choosing point P here, if we choose point P here or at center or at some other point, the answer will remain kq upon radius only. Why it is so? Because inside the electric field is 0, and whatever energy we spend to bring our unit positive charge from infinity, it is only up to surface. Because only up to surface we have non-zero electric field. Once we cross the surface, once we enter the shell, there is no electric field, so there is no energy spent, so work done is 0. So once you cross the surface, you are not spending any energy, and hence potential remains same. Whatever energy you spend, is only up to surface, and hence the potential is kq upon radius. Inside the shell, where your point is makes no difference. It is at center or from 1 mm from center or 5 mm from center, makes no difference. So as electric field inside the shell is zero, potential is kq upon radius. We spend our energy only up to surface, and hence potential is not zero, because up to surface we spend our energy. To come to the surface we do spend our energy, so potential is not zero. Potential is k cube upon radius, but once you cross surface, potential is uh, not changed afterwards. So if we conclude, we can say that for shell with radius r and charge q on it, if we want to know electric potential at some point, say inside the shell, it can be given as kq by r, where this r is radius, so kq upon radius. And what if you are talking about electric potential at some point outside the shell? Well, then it is given by kq upon distance. That distance matters. If you are at larger distance from the center, potential will be more. So that was the topic, and so with that, let us end. Thank you.